Today we're going to be talking about percent composition, and this is actually quite a bit easier than what you just did around stoichiometry. Stoichiometry takes a lot of practice to get it down right, to be able to go through and figure out where you're going, where you came from. Now, percent composition is relatively straightforward. There's a simple method, and I think that with probably 20 to 30 minutes of practice, you'll have this down solid. So we'll work through it pretty quickly. So on this first slide, what we're showing here is the formula for percent composition. So what we do is we assume that we have 1 mole of our substance, and then we calculate how many grams that is for the element we're looking at. So when we talk about percent composition, and let me just clarify this. If we take the example of H2O, we've got two different elements. We've got hydrogen and we've got oxygen. Now, the formula H2O tells us that we have 2 atoms of hydrogen to 1 atom of oxygen. But when we're looking at the mass, it is not 2 to 1. In fact, oxygen has a lot greater mass than hydrogen. And so in reality, in H2O, we're going to calculate what the percent mass is for hydrogen and for oxygen. And you'll see that it is actually much more oxygen by mass than it is hydrogen, even though you've got 2 atoms of hydrogen. That's just because hydrogen is very light compared to oxygen. So when we do percent mass, the simple formula is this. We put the mass of the element that we're interested in, whatever they're asking about, in 1 mole of a compound, and then you divide that by the molar mass of the entire compound. And in fact, if you're ever trying to figure out what to do with a percentage, it's almost always the same formula. On top is what you're interested in, on the bottom is the total. And that's the same here. It's the same as if you're looking at percent, like batting percentage or goal percentage. All of those are all the same thing. What you're interested in, how many goals you made, divided by total, the total shots you took. Okay, let's go over these 2 questions, and we will just work them out. They're easiest just seeing how you work them out, and then I think that you'll have that down pretty quick. Okay, this first problem asks, what is the percent composition of water? When you get a question like this, the first thing you have to do is you have to write down what the formula is. Now, sometimes, most of the time in your assignment, it actually specifies what element you want to know. Like, what's the percent composition of hydrogen in water? In this one, they just ask what is the percent composition of water, which means they want us to tell them the percent of each of the elements. So here's the method. Follow this method and watch this carefully. You'll understand why we do it this way as we go through it. So what we want to do is we want to assume 1 mole. Okay, and so if we have 1 mole of H2O, then we have 2 moles of hydrogen atoms. Now, if that feels uncomfortable, think about it. I've given this example a few times. It's like saying, hey, you have a dozen bicycles. And then the next question is, how many dozen wheels do you have? And the answer would be you'd have 2 dozen because each of those bicycles has 2 wheels. In this case, we have a mole of H2O. So how many moles of hydrogen do we have? We've got 2 moles of hydrogen. Okay, so let's write this out like this. 2 moles of hydrogen, and times that by the molar mass of hydrogen, which is 1.008 grams, and we get 2.01 when we round it, actually 2.02, my mistake, grams of hydrogen in a mole, in a total of a mole of H2O. Okay, the next one we put here is oxygen. So we've got 1 mole of oxygen. 1 mole of oxygen, let me make that a little cleaner. And 1 mole of oxygen, we times that by the molar mass of oxygen, which is 16.00, and we get 16.00 grams. And our total molar mass for water, which you guys have all seen many times, is about 18.02 grams. And by the way, when you're calculating molar mass, I expect you to go to the hundredths. You don't have to add on. Sometimes they'll have 3 and even 4 extra decimals. You don't need all of those extra ones. Just go to the hundredths. Okay, so our total mass is 18.02. So let's first figure out the percent by mass of hydrogen. So all we do is we take this number right here, the mass of the hydrogen, which is 2.02 grams, divided by the total molar mass, 18.02 grams, and we're going to times that by 100. I'm not a big fan of putting times by 100. I think it's kind of assumed, but they oftentimes have that. And so that comes out to be This comes out to be 11.2% hydrogen in H2Os, which is interesting. So only 11.2% of the mass is made up by the hydrogen. Okay, let me erase these little arrows, and then we're going to show what we're going to do next. Let's also do the same thing and figure out the percent by mass of the water. I mean, not the water, of the oxygen. So the oxygen here, we're going to put the 16 on top this time because we're interested in the oxygen. 16.00 grams divided by the total 18.02 grams, and times that by 100, and we are going to get 88.8 percent oxygen. So 88.8% oxygen and 11.2% hydrogen. Now, if we do this right, these should add up to 100 if we only have two different elements in the compound. So however many elements we have, if we add them all up, all the percentages, they should come out to be 100. And you can see here, these do come out to be 100. If you add these two together, they'll come out to be 100%. So that's a good sign that we did it right. What is the percent composition of magnesium chloride? Now, the important thing about this question is you need to phrase this, you need to get the correct formula, MgCl2. Okay, so if you just put MgCl, that's not going to work. So again, all we're going to do is do exactly what we did, where we assume 1 mole. And so if we have 1 mole of MgCl2, that means we're going to have 1 mole of magnesium. We times that by the molar mass of magnesium, which is 24.305. And that, of course, equals 24.305 grams. And then we have 2 moles of chlorine, and those are 35.45 grams each. And so 2 times by 35.45 comes out to be 70.9, I believe. Yes, 70.90 grams. And then we add those together and get 95.21 grams per mole as the molar mass of our entire compound there. Okay, so then we just have to break that up, do the exact same thing we just did. Whatever we're interested in, let's do it for magnesium first. We're going to put the mass of the magnesium here on top, 24.305 grams divided by the total, 95.21 grams, and times that by 100, and we're getting 25.5. We'll just go to 1 decimal place on that. 25.5% by mass for magnesium. Okay, and then the same thing here for chlorine. The mass of the chlorine in that compound is 70.90 grams, and that's, again, assuming we've got 1 mole. And then, of course, the total for a mole is 95.21 grams, and we times that by 100. And that came out to be 74.5%, and that is chlorine. So you can see here, if you add these up, they do come out to be 100. It's a really good sign we did it right, so we're feeling good about that. Okay, this last section is just a quick connection with earth science, and what it has to do with is minerals. And the reason percent composition is important is because when we look at minerals, minerals are essentially just large ionic compounds. Sometimes they can get quite complex, but maybe only one little part of it is what you're interested in. For example, it might be copper or gold or iron or silver or cobalt or a whole bunch of different metals, but they'd be part of these minerals, and we have to calculate the percent composition because then we can calculate whether it's profitable to mine that. Not only profitable, but also how does it impact the environment. So this is just an overview of the different metals that we mine. You can see most of what we mine is iron. We do have a lot of these that are well known, like copper and aluminum and magnesium. And then these lesser known ones, but have become very valuable, things like lithium that we've heard of, or cadmium. These are all important to technology, and so they become quite valuable when they look at minerals around the globe. This is just kind of a flow chart that shows some of the things to consider when we look at mining. We've got the ore body, which is the minerals that we're looking for, but then we've got the types of minings. We've got surface and underground. We have to have the processing of it, which has a lot of waste. And then the environmental impact has to be looked at when it comes to biodiversity, any contamination, and also human health. What impacts does it have on human health? This is kind of a dramatic view of the impacts of mining. I believe this is a copper mine, but you can see how that has, really changed the surface of the earth. And assuming it's probably changed the habitat of a lot of wildlife. So those are some impacts that have to be considered. Another impact is the human impact when you have places like in Congo, cobalt mining. You'll have forced labor and slavery, child labor, and very unsafe labor practices. Probably many, many people die in this type of mining. But of course, cobalt is needed for every lithium ion rechargeable battery. But I don't think we oftentimes consider the cost that goes into making something that we find very convenient. The convenience can have major costs that we don't realize. But when it comes to companies, their primary concern is going to be profit. And I'm not saying there are some companies that are very concerned about environment as well. But when it comes to profit, it really comes down to percent by mass. And of course, we calculate it just as we've talked about. And what we do is we then figure out how much does it cost to mine out a certain number of grams of that ore. And then we've got to say, what's the percent that we're actually going to be able to process from that's actually usable? And then we can do that calculation about profitability. All right, well, that'll do it for this unit, and you should be fully empowered now to complete the entire packet of 4.2. Hope you have a great day.